Hello everyone. Today we will be solving LeetCode number 1 to sum. In this problem, we have been given an integer array nums and an integer k. We have to find the indices of two numbers whose sum equals k. A point to be noted here is that there can be two identical numbers whose sum equals k, but their indices must be different. The problem also states that there is a unique answer present for every test case. Let us see the naive approach and then the optimized approach to solve this problem. Let's see the first test case as an example. Here, our target value k is equals to 9. If you look closely at the nums array, the first value is 2 and the second value is 7. 2 plus 7 is equals to 9, which is our target value k. Hence, we return the indices of these two numbers, which is 0 and 1 in this case. The most straightforward way of solving this problem is by finding all possible pairs between different indices of the array. If their sum is equals to our target variable k, then we simply return the found indices. Let's take the earlier test case as an example. Here, our target value k was equal to 9. To find all possible pairs of the nums array, we can run two nested loops within each other. Let the first loop be denoted by the variable I and the second loop be denoted by the variable j. While we are traversing through this nums array, we can keep track of the index I and index j. Nums I would represent the number at index I and nums j would represent the number at index j, whereas nums I plus nums j would be our final sum of both the numbers. Whenever this sum is equal to our target k, we can say that the index I and index j of those two numbers is our final answer. Let's go through it. A point to be noted here is that j must start one index after I, that is j equals to I plus 1. The reason being that we need two distinct indices in our final answer. Whenever we encounter the sum equal to our target k, we check the indices. In this case, you can see that index 0 and index 1 have values 2 and 7. 2 plus 7 equals to 9. Hence our answer is 0, 1, which are their respective indices. The overall time complexity of this entire operation is big O of n square. Why? The reason is that we are running two nested loops I and j within each other, and the operation of finding all possible pairs results to big O of n star big O of n, which is big O of n square. Whereas the space complexity is big O of n. The reason being is that we will be storing a maximum of n elements of the nums array. Let's code the solution up. Here nums represents our original array. So let L represent the length of our original array nums. If L is the length of our original array nums, then what we can do is we can run a single loop, the ith loop, in the range 0 to L. Similarly, we will run the nested loop, the jth loop, in the range I plus 1 to L. What these two lines of code are doing is they are creating individual unique pairs of indices of the nums array. The I plus 1 is there because we do not want the ith index and the jth index to be same. They must be different in their own accord. Now once we get all the possible pairs of the nums array, what we need to do is track the sum of the ith and jth index. How to do that? Simply nums I plus nums j will be the total sum of the ith number and the jth number. If this sum is equal to our target value, then we will simply return the indices at which this sum has occurred. This is the brute force concept of solving this question. The overall time complexity of this entire code is big O of n square because we are using two loops to find the total sum. But the space complexity is big O of n because total number of elements stored in memory is at max n, which is the nums array. When we run this code for the given test cases, you can see that it gets accepted for each one of them. And similarly, when we submit this code for all of the test cases present, you can see that it gets accepted there as well. A more optimized way of solving this problem is by using a hash map. By using a hash map, we can store the numbers and their respective indices in the memory and fetch them when required in the future. Let's see the logic. In this test case, our target value k is equals to 8. By looking at the nums array, you can see that 3 plus 5 is equals to 8. This is our original constraint. This can conversely also be written as 8 minus 5 is equals to 3. Suppose I was traversing the entire nums array and reached the final index. I know that my current index is 3 and the value, the number present at index 3 is 5. How much more would I require to satisfy the original constraint? That would be the target k minus current number. That is 8 minus 5 equals to number 3. My required number would be 3. But how exactly do I know whether I encountered the number 3 earlier? Is it present in the nums array? And if so, what exactly is its index? Here, HashMap would play an important role. By using a HashMap, while traversing the nums array, we can store the number and its respective index in the memory. And in the future, if we encounter the required value in the HashMap, we can simply just extract the index of the required number. In this case, it would be 0. And our final answer would be 3, 0. Let's take a step-by-step demo on the previous test case. We will be running a single loop from the start to finish of this particular nums array. While we are doing that, we will also be checking the original condition, that was the target k minus the current number x must be equal to the required number y. With this, we will also keep track of a hash map which stores the current number x and its respective index in the memory. This would be required for the future use to directly extract our required index. Let's take one step at a time. Originally at index 0, our current number was 3. The required number would be 8 minus 3, that is 5. Is it present in the hash map? No, it is not present. So what we will do is we will set the current number and its index for future use. That is 3 is equals to 0 in the hash map. Now going to the next index. At index 1, our number was 2 and the required number would be 6. Is it present in the hash map? No, it is not present. So we will set the current number and its index in the hash map, that is 2 equals to 1. Going to the next index. At index 2, our current number is 7 and the required number would be 1. Is it present in the hash map? No, it is not present. So we will set the current number and its index in the hash map. Going to the next index, index 3. At index 3, our current number is 5 and our required number is 3. Is it present in the hash map? Yes, in this case it is present. You can see that the number 3 was present earlier from our traversal. And what exactly is its index? You can see that the index 0 is directly associated with the key number. So we will directly return the index 0 from memory. That is our first answer. And what would be our second index? That would be the current value or the current index at which we were. That is index 3. And finally, our answer would be 3, 0. This entire operation takes a time complexity of big O of n. The reason being, we are running only a single loop on each element of the nums array and storing each element in the memory. In worst case, we are storing at max n elements of the nums array. We are taking a space complexity of big O of n. Let's code up the HashMap solution. In Python, we initialize the HashMap using the keyword dict, which refers to a dictionary. In languages like C++, you can use an unordered map to do the same job. The core logic is the same. Now once the hash map is initialized, what we will do is we will run a loop from 0 to L on the nums array. So I will say for index in range of length numbers. Now once we are running the loop, the current number of the current index would be nums index, right? And similarly, the required number which we require, that would be the target minus the current number, right? If you remember earlier, when I was explaining the entire slide. 3 plus 5 equals to 8. If our target is 8, then that means 8 minus 5 is 3. That is the same logic, nothing different. The current number represents the current number at this index, and this would be the required number to satisfy the constraint. Now, what we do different in this case is that we check if the required number is present in the hash map. If the required number is present in the hash map, that means that we know that the required number has been already found earlier during traversal, and we also know the current index of the current number. So by accessing the index from the memory, we can simply return here the current index and the index from the memory, which would be the index of the required number. This index right here represents the current index of the current number, and this entire thing right here would represent the index of the required number from the memory. Simple. But what if the required number is not present in the hash map? That means that we still need to traverse the remaining nums array to find the answer in the future. And for that purpose, what we will do is we will store the current number in the hash map for future use. So we will say hash map current is equals to index. What this means is that we will store the current number as the key in the hash map and the index as its value in the hash map. This entire approach right here is the hash map approach to solve the two-sum problem. This entire approach takes a big O of n time complexity because we are just running a single loop on each element of the nums array. Do note that the operation of finding the required number in the hash map is a big O of 1 or constant time complexity operation. Hence the overall time complexity of this entire code does not change from big O of n. Whereas the space complexity still remains big O of n because we will be storing a maximum of n elements in the hash map for future use. When we submit our HashMap code, you will see that it gets accepted in just 36 milliseconds. Whereas if you remember earlier, the brute force approach took almost 2000 milliseconds to complete the same code. Using HashMap, we are able to perform the same operation in linear time complexity and linear space complexity, whereas the brute force solution took quadratic time complexity to complete it. Hence, there is a great optimization in the overall performance. That's it for this problem, guys. Thank you so much for watching, and I will see you in the next one.